So again, the point is conservation of momentum. So originally the cars were at rest, touching each other. They're connected, usually by the Velcro. But that meant that the momentum before you released the plunger was 0. Afterwards, the cars were spiriting off in either direction. Something like that. Now, each car had momentum. But what we're trying to show is that the momentum after you release the plunger is equal to the momentum before. Now, to do that, you have to realize that there's definitely a positive direction and a negative direction. We'd have to assign negative to one of these cars. But if you have two numbers that are supposed to sum to be 0, those two numbers have to be of equal size. Do you guys understand that statement? Are you sure? Maybe that's where it's confusing. Because I wrote this next, that if these are equal, if they are equal, then this would have to be true. Don't let the absolute value bars scare you off. It just means that these two numbers are the same size. I know that one has to be negative, but I know that. I watched the lab. One went one way, one went the other. So if these two are the same size, we can state that the momentum after the spring was released is 0. Now, unfortunately, we didn't measure velocity. Since we didn't measure velocity, we need to consider our assumptions about this lab. So let's consider at least one assumption that we made. One assumption was we took every reasonable precaution to make sure the track was level and that the actual track portion that we used was short. That way, the velocity was constant. Meaning when the cars were separating, they weren't speeding up or slowing down. But for the duration that we observed them, the velocity was constant. If that's true, there's no acceleration, and we can state that velocity is simply how far they went divided by how long it took to get there. Right, with no acceleration, that's true. Bless you. That's funny because the thank you is just as high as the sneeze. So that means that m1 delta x1 over delta t1 has to be equal to m2 delta x2 over delta t2. Now that's looking complicated. I know, way complicated. Which brings me to assumption number 2. Assumption number 2 is we did trial and error to try and find a place where we could start the cars so that when they separated, they both hit the ends of the track at the same moment. This was important because we didn't make the distances the cars traveled the same. We made the time that the cars traveled the same. That way we could state that delta T1 was equal to delta T2. Does that make sense? Do you understand what you did in the lab? You moved it back and forth until they hit the edges at the same moment. So that from when you hit the plunger to when they hit the edges, T was the same for both cars. Now if that's true, that means they're all equal to the same, it's equal to the same number, delta T. They are the same number. So I could take away that little subscript. Because they're the same time. Now this is what's important. Here's the big takeaway. That means if they're the same time, I can get rid of them because they're the same on both sides. Allowing me to write this. M1 delta x1 should be equal to M2 delta x2. So I started from a first principle, conservation of momentum, and through a little algebra and dealing with our assumptions, we came down to this question. Now, we are not actually comparing the momentum of the two cars because we can't get the velocity directly. What we are doing is comparing something that is proportional to the momentum. Should these be relatively equal, it would be like saying the momentum was relatively equal. So we're comparing a proportion. So to do that, I want you to realize you took this data, right? Car 1, you took M1 and distance 1. Car 2, you took M2 and distance 2. You have this data. In fact, Sophie, give me something in the middle. One of your pieces of data.
500 grams and 48 centimeters.
This is in the middle?
Oh! Okay, like 1,250 grams and 45.5.
1,250 and
40 centimeters.
40 centimeters. And give me the corresponding M2.
1,000 grams and 56 centimeters.
Okay. So here's what you need to do next. You have to decide whether these two sets of data are equal or not. This part I did not do in another class. I'm just doing one here. What I would like you to do to show how far apart they are, or to see if they are equal, is just compare them. There's a number of ways to do a comparison. We can do a ratio and see how close the ratio is to 1. I don't believe that really gives us the kind of comparison that works best. I would like you to do a percent difference calculation, which we've all done before. Now, what I ultimately want you to do, let me just kind of separate this out, is I want you to calculate the percent difference average for the experiment. You'll calculate all 7 or 8% differences and then average them all for the whole experiment. I have no idea how close you're going to get to 0, but if they are equal, the percent difference should be 0. They're not going to be 0. There are lots of places you screwed up, I'm sure. Little things, like, did you touch the plunger with your finger? Your finger friction, it probably slowed down the car that you touched. Did you make sure the masses are all pushed towards the center so that they wouldn't slide on the pan? Was your track actually balanced? Were the cars actually the same? There are lots of little things that could be wrong here. But ultimately, we want to see how far apart these two numbers are. Now, I'm under an assumption that you guys know how to calculate percent difference. It's how far apart two numbers are divided by the average of the two numbers. And my concern is that you don't know how to do that either. So, and even in the other classes, I wrote all this out. I said you're going to take M1 delta X1 and subtract M2 delta X2. You're going to take the absolute value because we don't care whether it's bigger or smaller. We're just looking at how far apart they are. Then we're going to divide by the average, M1 delta X1 plus M2 delta X2, all divided by 2. That's the average. And I hate to say this because this belittles all of us, but you want to convert that to a percentage. It already is a percentage, but some people like to put the times 100 there to make them feel better about themselves, because percentage means out of 100 or compared to 100. So I would normally end my discussion right there, but we're going to take it one step further. We are with, let's see, Sophie, you multiply those two numbers together. And Ava, you multiply those two numbers together.
1,056.
Yippers. It's 5,600. 5,600.
Oh, yeah. No.
Oh, 56,000. Okay, I'll believe you. And what's 1,250 times 40? 50,000. So those are the two numbers we have to compare. Now, you didn't convert anything into grams, you didn't convert anything into meters, but we don't have to. We're making a comparison of these relative numbers, and it'll be okay. If you did convert and use meters and kilograms, it's fine. We're going to get the same comparison anyways. It'll be the same percent difference. But this is going to be the absolute value of 50,000 minus 56,000 divided by the average of 50,000 and 56,000, which is 53,000. I'm not going to type all that in there. This is going to be 6,000 divided by 53,000, which is 6 over 53, which is what percentage? Which is what percentage? Which is what percentage? 11%. Thank you. I don't have a calculator here. I'm waiting for you guys to do that. Like do the 6 divided by 53. It wasn't a whole lot. Maybe this is harder than I noticed. All right. So I have done 1 of the piece of data. You guys have 6 more to do, or 7 more to do if you took enough data. Now, any question, and I always say this, and usually there's silence, but let's see. Any question of what we've done to this point? All right, so listen closely. They are 11% off. You're going to do this for all 8 pieces of data. And then take that average, and when you're done, you will have the average percent difference over the entire lab. The question you have to ask is how low does this percentage have to be for you to say that they are reasonably equal given error that's introduced in the lab? I will not give you a threshold. In fact, what I want to read is how you decide whether this is low enough to say you demonstrated conservation of momentum or not. Is 11% low enough? I'm not going to make the judgment. You make the judgment. You decide. And then explain yourself. Ultimately, you have to understand that unless you get 0%, you can't show or demonstrate pure conservation momentum. What you're really asking here is this demonstration within the likely amount of error that was introduced in doing this lab? Is it reasonable to assume that you were close? I don't know if 11% is high or low. I mean, I have my own ideas about it, but I think you guys need to have your ideas about it. Please understand that you are not graded up or down based on whether you showed conservation of momentum. You are graded up or down if your data is sloppy. And I don't mean messy handwriting. I mean if it's clear that you were not careful. You weren't taking your time to make sure the cars moved and hit the sides at the same moment. I already have that tucked away. When I walk the room and you guys are taking data, I'm taking notes at the front of the room. I know who was being careful. I know who was helping. I know who was sitting there and didn't touch anything. I know who was asleep, and I know who was on their phone. I keep those notes at the front. So I really can take a look at your lab and know whether you really participated or not. But the write-up portion, that's where you decide and you use your analysis to decide whether that's close or not. All right? Any questions about that? I would like to do one other thing with this, and it's a little bit more work, but it's no more calculation. I want you to make a comparison, and I'm going to go to another page about this real quick, just have some place to write. I don't know the answer to this question, by the way. I'm using your data as a means of getting it. I believe that when one of the cars became more massive than the other, that there's a likelihood of an increase in percent difference. Meaning when the cars were probably the same mass, it was probably easy to show that the percent difference was low. But as one car became heavier than the other, I think that the percent difference also increases. Does your data back up that statement? I'll say it again. But as the difference in the car's mass increased, was there also an increase in the percent difference? I think that the cars are not as balanced as the manufacturer tells me they are. And that the actual bearing wheels in there are highly affected by friction. I also think that the mass warps the track. And one of them is more massive than the other, just like having a big person on a bed with a small person. The small person is affected by the big person and rolls into the dent. I think something's happening like that in a lab. I want to know. So answer that question. As the cars separated in mass, was there also an increase in the amount of error? Second lab was two-dimensional, but you measured distances. Again, I want to highlight that before we talk about the actual lab thing again, in that we're going to measure distances, but do you remember way back when physics wasn't so hard, that was true? Does it look familiar? The whole, a ball leaves the table at a horizontal velocity. Where does it land on the ground? It's like we did that. This would be the range. The one thing I want to point out is that whether the ball had a collision or didn't, the time it took the ball to reach the ground was based on the height of the table, not how fast it was going. That should be familiar to you. That the vertical velocity was 0, whether there was a collision or not, and therefore the balls took the same amount of time to reach the ground. That being true, what you produced as part of your lab, what do you mean no? It'll be on YouTube later, where all of my Ugandan followers will watch it closely.
I thought they stopped watching.
Yeah, they've kind of stopped watching. It's disappointing. Back when I was a favorite in Uganda, I was very proud of my Ugandan watchers, but now I've lost their physics respect.
Or they graduated.
Maybe, but there's always another kid. Okay, does this look like yours? Kind of, a little bit? Yeah. Now, I want to point out that you actually have 3 distances here. We have distance A, distance C, and distance B. This is how I put it on your paper. With, a bunch of dots here, a bunch of dots here, and a bunch of dots here. A represents the path the ball took if there was no collision. B and C was after a collision. So that all makes sense? So here's what I want you to consider. Based on what I just described, that the time was the same for all of them. A represents a range, as does C, as does B. They're ranges. But they would all have taken the same amount of time to reach the ground, which would make this the velocity for A, this the velocity for C, and this the velocity for B. Do you note that since the times are all the same, I can compare the ranges, and that'll be okay? It'll be proportional to the velocities. Is that okay? Do you understand what I just said? Yes, ma'am.
For the B, what does that say that B times R?
B is equal to R over T again. So this is like the range of B, this is the range of C, and this is the range of A. I'm just going to slip past this and remind us that we're just going to look at the lengths. The lengths are proportional to the velocities the balls had as well. Now, I told you that you should go through here and measure this angle and this angle. And from there, you can figure out that length. It's going to be C sine this angle. You can figure out this length, which is going to be B sine the other angle. That's what was on the board. Also, I said you can find this length, which is going to be C cosine the angle, and this length, which is going to be B cosine the other angle. All of that was on the board. Now, let's back away from that for just a minute and consider what really happened, what this picture really shows you. What this picture really shows you, and I'm going to turn it sideways if I can. What this picture really shows you is that the ball had a momentum before the collision that's equal to the length of the white line. There was a target ball here that when struck by the first ball had a momentum in this direction, while the original ball ricocheted in this direction. Your picture is a picture of the collision. This shows you it spread out, so you can see what was happening before and after. More importantly, before the collision, there was no left or right movement of the ball. Do you guys see that? It was just vertical. So after the collision, the sum of the left and right movement has to be 0, because there was none before. Whatever momentum was to the right, there had to be an equal and opposite momentum to the left. At the same time, the momentum upwards. I'm using the word upwards, but it's really just the vertical momentum here. It has two parts. There's the part from the red ball and the part from the blue ball. They need to add up to equal what was there before. So what I'm looking at really is that there's a certain amount of momentum to the right that should be equal to the momentum to the left. You should compare those two. Show that they are the same size. There's a certain amount of forward momentum from the red ball and a certain amount of forward momentum from the blue ball. And I'm using red and blue because of what I have drawn here. But one was the target and one was the ricocheting ball. These should equal what we had before the collision. That's what you should be looking at. Now, that alone isn't so bad. You just saw how to calculate it. And I know it involves cosines and sines, and that can be tough. So let me give you a brief alternative. A way you can do this without having to deal with sine, cosines, or angles. With your with a ruler, you can actually take your measurements probably more accurately than you can with by measuring the angle using a protractor. Take your ruler, slap it on your paper, and draw a perpendicular line to here. Do the same thing on the other side. Guys, I'm not going to I'll let you actually do this in the time that we have. You just measure those distances. If you ensure that these are right angles, this should be equal to that. Should be. Find the percent difference. See how close it is. That's not enough, though. With these lines drawn in, measure this distance and measure this distance. This is the momentum of the target ball. This is the momentum of the ricocheting ball. These two momentum should equal the momentum without a collision. Should. It may not, but should. Compare them. Take the sum on the right and compute the percent difference with the momentum on the left. Now, a couple of pieces here. that are, I think, hard. You had to have balls that had the same mass. If you use two different marbles, your data will not work like this. The difference in mass skews the data towards the heavier of the two marbles. This is why you needed to use two marbles that were the same. If you use different marbles, you need to know how close in mass the two masses are, or you need to know the mass of the balls. Notice this whole analysis never dealt with the mass, because we assumed mv for the ball before the collision equaled mv for the two balls after the collision. If all the masses are the same, they would have canceled out, and all we have to compare are velocities. That's why the mass of the ball wasn't necessary.
You have to calculate the percent difference for the vertical and horizontal?
Yes. But you only have to do it once for each. It's not like you have 8 of those to do. So the one thing to consider though is look at what you're trying to compare it as being the same. You're trying to compare these two green lines and see if they're the same length. And you're trying to compare the sum of the yellow lines and see if it's the same length as the white line. I'm using the colors because that's what I have here in front of me. Does that work out for you guys okay? All right. So